Um, Hello everyone. Yeah, that's fine. Yeah, that's okay. Nice talking to you as well. How's everyone else doing? Any exciting thing happening over the weekend? Nothing exciting? Anything happen? I took a nap. Well, yeah, I really need one myself. I'm doing very well. Weekend was mostly with family, so that was good. But yeah, still working from home as everyone is doing. Sleep after a week of late nights on assignments and work. Yeah, I hear you. I think well, for me, was it what, Monday or was it Sunday that I slept more than other days usually? I think it was Monday. I just decided to sleep in a little bit more, a couple more hours. No, it was Sunday, sorry. I usually wake up very early in the day, so but Sunday was kind of an exception there. Well, I hope all of you are doing great and you had a nice weekend. Do you have any questions for me about anything in the course so far before we begin our lecture today? All right. I believe that the grades for assignment 1 are out. So better check them out on eClass and see how things are going. If you find any problems or issues with your assignments, please reach out to IFAZ or myself. I'll be happy to help you out. Otherwise, we can start our lecture for today. So, continuing on our discussion about call graphs on Thursday last week. So we basically went through a few introductory slides about call graphs, how they are important, how they are used in almost all static analysis tools, because they are the data structure that allows the analysis to reason about how to cross method boundaries. If you have a method call, which method would that call, may that call be dispatched to at runtime? So a call graph is a data structure that would tell you that information. So we have been through a quick example there, and another quick example to build a call graph in a Java-like method. Main problem with call graphs that can make the data structure increase exponentially in size to the extent to being unuseful or useless is polymorphism. So the more polymorphism support in your language, the more potential methods that could be called at runtime at a given call site, and the larger the call graph gets. And then we went through a couple of scenarios where ideally you want to compute the call graph that exactly matches the runtime behavior of the program. But again, this, like everything else in static analysis, would reduce the halting problem. So to over-approximate that runtime behavior, researchers and practitioners usually resort to a whole program call graph, so analyzing the application part of the code in addition to all its library dependencies. Sometimes those library dependencies may not be available, or they may not be feasible to be analyzed within a given limited resources. So one way to over-approximate them is to conservatively say, well, the call graph basically contains all possible methods that could be called at that point, which would be highly imprecise. Another way, the other extreme, would say, well, I don't know what these libraries are doing, so I'm just going to ignore what their effect is, and I'm not going to bother with what they could do in the program, whether with regard to field accesses, method calls, or local variables, reads or writes, and so on. But then you're going to get an incomplete call graph, which is unsound, meaning that there could be some potential methods that are called at runtime that will not be represented in this call graph, which would mean that you're going to miss some runtime behavior of the program. and we don't want that. So because that means that the call graph would be incomplete. So following that, we, I think, ended the lecture on Thursday by introducing very briefly, just basically listing out the names of 4 call graph analysis algorithms that we're going to go through in the lecture today, and seeing how they are actually implemented in one of the most famous static analysis frameworks, the SUT analyzer or the SUT analysis framework. These algorithms are listed there on the slide in an increasing order in terms of precision, and we're going to go through each one of them, see what the benefits, what the pros and cons of each one of them, when to use one versus the other, and so on and so forth. And then most probably we're going to have on Thursday a hands-on lecture with just how actually to generate some of those analyses, some of those call graphs using each single one of those analyses that we're going to discuss today in class, and we're going to see how we can actually write code that will generate those call graphs, what would be the practical uses of each one of them and how they compare to each other, and a few other things related to generating call graphs in practice, not just in SUT, but maybe also we'll go through the WALA analysis framework. But I will reserve that to Thursday. So on Thursday, if you want to try things along with me, we can do that in the class. I'll make the code available to you so that you can follow along as well beforehand if you want to try things out before the class. And if you have any questions, as usual, just ask me whenever you have any questions. Speaking of making things available, I think right now on eClass you should see a new link on the home page that is basically lecture slides, and that will take you right to the GitHub repository where you can check out all the slides that I'm using for the course. I made all the keynote slides available as well as PDF printouts for them in case you don't have Keynote or you cannot use the online iCloud viewer for it. I also made the handout that IFA made available to students since last semester or last year, since we told this, available to you as well. So the handout is related to lattice definitions. So I think it might be useful to go through it. It's a LaTeX file, you just need to compile it, and you will get the PDF right away. If you're having trouble with that, I can make the PDF available as well, that's fine. But all the slides are available, all the PDF printouts of them are available. If you have any questions, please let me know. But everything that I'm using in the class is available to you as well. All right, so now that we have gone through this brief introduction, let's actually start discussing one of the first call graph analyses that we're going to talk about. So the first call graph analysis that we're going to discuss today is class hierarchy analysis. By the way, for every one of those analyses, at the bottom of the introductory slide for it, you will see a citation of the first research paper that introduced this call graph analysis. So if you want to learn more about the analysis and how it is, how it was presented in a conference paper as a research paper, and what the original authors of the analysis wanted out of it, I would recommend checking out those papers. They are a bit old, but they were the papers that pioneered all those call graph analysis algorithms. So you better check them out. This is also a good exercise for you to prepare for the paper seminars and the paper readings that we're going to do in the course later on in the second half of the course. So the first analysis that we have is class hierarchy analysis. So I'm going to show each one of those call graph analyses with an example. So in here we have an example where we have a main function in Java. Given the verbosity of the example, you can tell that this is Java. Public static void main creates a collection based on some argument that is passed to the main function, and then it will call the method add with that element on that collection. The function make collection will basically have a switch statement or an if-else statement on the given type, which is a string. If it's a list, it will create an array list. Otherwise, it will create a hash set. So you would expect that in this add function will be called, it will dispatch to a different method depending on the type that is given to it by the main method. So let's actually create the call graph for this and let's see what happens. So the first thing is the main method on the first statement here is going to call make collection, right? It's a function, it's a static function. We know exactly, in static functions, it's a direct call. There is no dynamic dispatch, there is no polymorphism. You know exactly which method is going to be called. So in this static call here, we can just add make collection to main. So far so good. Now for the c.add, in class hierarchy analysis, given the name of the analysis, it only looks up the class hierarchy that is available in the program. So in this case here, it will look up the class hierarchy and then see, okay, now I have, like if you see here, it will check that, well, the type of C is collection. So I'm gonna check out every single method add in a class that is either collection or one of its subclasses, which is the class hierarchy in the program. And based on that, I'm gonna figure out all the possible methods, the add methods that may be called at this call site. So here you can see, this is an actual snapshot. If you do this if you have this example, copy paste it on Eclipse or IntelliJ and figure out the class hierarchy of class collection, you're going to see all those classes. So you'll see abstract collection, abstract list, abstract set, RADQ, linked values, value collection, various types of values here, check collection, collection view, observable variables. All these classes will show up here. So a class hierarchy analysis at this call site will tell you, well, I can call array.list.add, array.list.add, hashset.add, stack.add, vector.add, and so on and so forth. Linked list.add, and so on and so forth. Plenty of methods there. Too many methods, in fact, right? But again, the analysis just looks at the class hierarchy, nothing else. So on one hand, the analysis is very simple, right? Just give me the class hierarchy. I don't need to analyze any code. Just tell me what the class hierarchy is, and I'm going to tell you an over approximation that is sound, right? So in one of those green zones in the lattice of solutions that we talked about in the previous lecture. So it is very simple. It is sound, correct? So it is not going to miss any potential runtime behavior of the program. It's pretty fast to compute. There is no data flow, there is no flow functions, there is nothing really that needs to be, no fixed point solution, no data flow algorithm that is going to be run, just scanning the class hierarchy. The input to this analysis is only the class hierarchy, and we're going to see in a minute here why this is an important pro point for class hierarchy analysis. However, the big drawback of class hierarchy analysis is that it is really imprecise. There are a lot of edges that are going to be returned by the class hierarchy analysis that will never occur at runtime, right? So if you go back here, stack.add, for example, I know from the program that stack.add is not even there, so why bother? But it's still a valid solution, it's still a valid over approximation, however, it's an imprecise one. So this class hierarchy analysis is more on the side of highly imprecise solutions or highly conservative solutions for call graph analysis. All right, so far so good. Thumbs up on Zoom if you don't have any questions. All right. Cool. So this is a simple analysis, but we know that it is imprecise. We've just seen that how imprecise it could get. So let's refine some of the results that we're getting from the class hierarchy analysis. So the next analysis that we're going to discuss is called rapid type analysis, or in short, it's called RTA. Class hierarchy analysis in short is called CHA. So you're going to see that these acronyms used quite a bit in the literature and also in the analysis frameworks as we're going to see them. So the rapid type analysis will do exactly the same as a class hierarchy analysis. The only difference is the following. So it will still look at the class hierarchy only, but it will look at the class hierarchy and add to it one smart feature. It will basically figure out, well, why do I need to bother with all those classes that don't exist in my application? I'm never going to create objects of these types because they are not here. I only see two objects that are being created, new array list and new hash set. So I can only call either this or that. I don't need to bother with all these other classes. So still, I'm looking only at the class hierarchy. I'm kind of scanning the code, but I'm not doing really data flow analysis here. I'm just looking at the objects that are being created. So I can do basically a quick grep kind of analysis that looks for new instructions and then see what kind of class or which classes are being called or being created in those instructions. So it's not really a data flow analysis or a sophisticated analysis or even an interesting analysis. It's basically a grep over the bytecode in case of the Java program that we have here. Or for the source level analysis, just look at all the new instructions and see which classes are being created. So that paper or that analysis was actually first introduced in the context of doing analyses for C++ virtual functions back in 1996 and was published at one of the major conferences in programming languages and systems called OOPSLA in 1996. And then it has been developed afterwards and expanded to and extended to many other languages, Java included and Scala and almost all the other languages that are available out there that has analysis frameworks for them. So rapid type analysis in short, it is rapid, so it is still fast, hence the name. It is still sound and correct. So again, it's one of those results or fixed point solutions that exist in the green zone of that lattice that we talked about in class last time. The call graph is much, much smaller than the class hierarchy analysis because we are eliminating a whole bunch of edges and nodes from the graph that don't need to be there, just by looking at the constructed objects in the analysis. Problem with this analysis though is that it does not handle variable assignments. So what if those constructed objects are being passed around across assignment statements? So you create an object, you assign it to another field or to another variable, and you pass it along as a parameter to a method. So there is no data flow that is being tracked in the program, or even pointer tracking in this program, in this analysis here. So this is the major downside of rapid type analysis. Otherwise, it's pretty much the same as class hierarchy with the added benefit of eliminating a whole bunch of imprecise edges and nodes. So far, so good. Any questions about CHA or RTA analyses? All right. So what do we do now? Well, we want to support tracking those objects and pointers across variable assignments. So the next analysis we're going to talk about is variable type analysis, or VTA for short. So what does this analysis do? The main idea is going to be the following. The main idea is going to be we're going to propagate types from allocation sites to where those variable references may exist, to potential variable references. This analysis was first introduced by a whole bunch of people from the University of McGill, or McGill University in Montreal back in 2000, again at the same conference, OOPSLA, led by Vijay Sundarisan, who is now one of the pioneers of the JIT compiler team and the Java runtime team at IBM in the Toronto lab. The late Laurie Hendren, one of the pioneers in programming languages and compiler construction in Canada and in the whole world actually, and Patrick Lamb and a whole bunch of other people that contributed to this analysis back in 2000. So what do I mean by propagating the types from allocation sites to potential variable references? Let's have an example. So first, we're going to start with a pre-computed graph. And remember this because it's going to come back to us later in a few minutes. So we need to start with a pre-computed graph, let's say CHA. We're going to build a type propagation graph. So it is not a call graph. It is a graph that tracks how types will propagate throughout the program. The third step is going to be collapse strongly connected components. We're going to call them SCCs. So strongly connected components are components that have cycles in them. We're going to collapse them into one node in the graph. Then we're going to see why. Then we're going to get, after this point, we're going to get directly a cyclic graph or a DAG. Then we can propagate the types across this DAG. And then we're going to have our final type propagation graph. And based on that graph, we can answer questions about what methods could be called at a certain call site, because I can tell the type of objects that those methods are being called on at that point, and I can tell you, well, it's going to be any method that is declared in any of these types. So obviously this analysis is more involved. There is some tracking of types, there is some tracking of assignment statements, there is some tracking and more heavily involved analysis of the code rather than just scanning the class hierarchy. So we're getting deeper now into further precision and further analysis that is being done on the code. So let's have an example. In the first step, why is it important to know or to start with an initial call graph? The reason why it is important is the following. So at this call site here, q equals o.foo and I'm passing p as a parameter. If I'm scanning this code to figure out all the types to create the initial type graph, I need to know at that point which foo method am I going to call, right? Is it going to be y.foo, x.foo, maybe some other foo method? I don't know. So the only way I can tell is if I have a call graph to be able to know which method I should start analyzing at this point, so that I can gather all the types that are being instantiated at that method, and then I can continue with my type propagation. So even though that I'm doing actually call graph analysis, this call graph analysis VTA needs an initial call graph to bootstrap itself. So this is one potential drawback of the analysis. Like, you need to start with an initial call graph, and it seems now that we only know two of them. So maybe we can start with RTA, or maybe we can start with a CHA call graph. But we have to start with one. We cannot just bootstrap the analysis without having other analyses, without having an initial call graph in there. All right, so step 2, we're going to create the type initialize the type propagation graph. So how are we going to do this? So here I'm showing the code that we're going through, and this is a very generic language, no specific syntax there. And here I'm showing this here shows the class hierarchy of the classes that we have. So class A is a superclass of B, which is a superclass of C. So I'm going to go through every single statement, and I'm going to see, based on the assignments of local variables, which variable would have its types propagating to the other variable. So the first here, well, the first assignment statements, I mean, all these are constructors, so they are not really local variable assignments, but rather constructor statements. You're allocating, or allocation size, or you're allocating objects. So we're going to skip through them. So the first statement that we really want to look at is A1 equals A2. So what does that A1 equals A2 does? Well, it says that whatever types that A2 has are going to be propagated to the set of types that A1 may have. And we're going to follow along with that. So in that second statement here, what do you think I should add to the graph? I think it might be easier if you just use voice in the Zoom call to do this than typing it up. So in that second statement, A3 equals A1, which nodes and edges should I add to the graph? Anyone? So just follow the definition of the assignment statement. So what does this statement say? That statement here, a statement that is labeled by 2. Yeah, exactly. New node, I'm gonna create a new node A3. I think that was Jacob, right? Thanks, Jacob. So we're gonna add a new node A3, and then we're gonna assign A1 to it. So that's exactly what I'm gonna have in the type propagation graph based on this statement. So all the types in A1 are going to go to A3. And now if I have A3 equals B3, what should I add to the type graph now? So I'm at the third statement, and it says A3 is equal to B3. What should I do now? New node B3, sorry, say that again? Yeah, that's exactly right. Yeah, so A3 is going to have 2 incoming edges. B3 now is going to point to A3, meaning that all the types in B3 are going to propagate to the node A3. Now, what happens with that statement here? B3 is equal to the typecast of A3 to B. What do I need to add here? A3 is going to point back to B3, right? And you're going to see now where this collapsing of strongly connected components come in play, right? So in the last statement, this is pretty obvious. B1 is equal to C. I'm going to just create 2 new nodes, C and B1. I'm going to assign C to B1. Then in the third step, sorry, in step 2, so now that I have created all those nodes and edges, I need to as well figure out what is the initial values that I can deduce from the allocation sites to assign to nodes. So I can tell, for example, that based on those assignment object allocations, I can say that A1 is going to have the set of A, A2 is going to have the set of A, or a set with an element A, B1 is going to have a set with B, and B3 is going to have a set with B, and C is going to have a set with C. So this is what I'm going to assign all of them to look like, right? All of these nodes are going to have those initial values. Then the third step is we should collapse all these strongly connected components. So a strongly connected component is a component where all the nodes are connected with a cycle. So there is a cycle exists. So collapse all those cycles. So here I have A3 and B3 as a cycle. I'm going to collapse them to be in the same node. So I'm still going to have them A3 and B3 as nodes in my graph, but I'm going to treat these two as one node virtually, basically, in my type propagation graph. And the reason we are doing that is basically to allow the analysis to terminate, because if we run the next step with the type propagation across the graph, the assumption is that it's going to be a directly acyclic graph, so that the analysis will terminate. If it is not a directly acyclic graph, the analysis will never terminate. So it will keep going back and forth in cycles until you get a Stack Overflow exception, or you get a runtime exception or something. Excuse me. So after we do that, we're going to start propagating the types. So here, I'm going to propagate that type A to the eventual node, and I'm going to propagate the type C into that node here. Notice that this virtual node didn't have any types assigned to it, so it got the set A directly from A1. B1 initially had the type B in it as its own set of types, but then when C propagates to it, I'm not going to overwrite that set that already exists in B. I'm going to add to it. So I'm not going to remove elements from it, but rather I'm going to add to it. So you can think of this again, relate this back to the lattice of solutions that we had, and lattice theory that we have discussed in the last 2-3 lectures. When you're merging facts together, you're not erasing ones, but you're trying to find the least upper bound of the merge operator or the join that you're computing. So basically here, think of this as the following: you have the set of all types, right? In your the set of all possible types that you have, and you're defining your join operator to be the union operator, the actual set union operator. So that's why B join C is going to be the set B unions the set C, which is the set of B and C. So everything is related back to that lattice theory that we have been discussing in the last couple of weeks. And everything is determined based on your merge, your join operator, what your lattice is, and what the elements of the lattice is. So that's why here B1 is going to have B and C, right? So far so good? Any questions about this? You may get a different result, by the way, if you define your lattice in a different way, or if you define your join operator to be different. That's up to the analysis engineer to determine that based on the kind of result that they want to get. So now that we have types for all the nodes in the graph, this is when the analysis, we know that the analysis is done. So there's no further propagation that needs to be done. So obviously we have a more precise analysis than RTA because we are tracking exactly the points to, we are tracking exactly those variable assignment in my program. It is kind of relatively fast. We're still not doing fully blown data flow propagation yet. We are only tracking the assignments of variables to each other. We're still not defining flow functions or doing data flow analysis yet. However, one of the biggest drawbacks for VTA is that it requires an initial call graph, whether RTA or CHA, and it is also field-based. So the analysis is field-based. So what does it mean that the analysis is field-based? We're going to see that actually in a few minutes in today's lecture. What does it mean that the analysis is field-based, and how does that affect the precision of the analysis? It has to do with how the analysis would handle field accesses. So we'll get to that in a few minutes. Do you have any questions about CHA, RTA, or VTA? You mean this one here? This one? So, I mean, it doesn't matter what actually A3 or B3 has, because for the analysis, it's going to treat the strongly connected component as one node. So even if you assign like B here to B3 in the previous step, this doesn't matter anymore, because now I only see one node, which is A3 and B3 together as one node. So that value set of A is going to be it's going to be the value if let's say in a later or some other analysis is using the results of this analysis and then says, okay, now what is the types that B3 may have? It's going to be the type A, because of the fact that it is part of a strongly connected component. Okay. Does that answer your question? Okay, cool. Any other questions? Sure. What do you mean? How did I decide between A and B? Right? Yeah. Right, so here's the thing. So here in step number 2, I looked at all the nodes that I have, right? And then for the strongly connected components, I do not assign any values to them, any initial values to them. So the fact that the strongly connected component got the set of A is not because I chose between what A3 may point to or what B3 may point to. In fact, that came at a later stage. So it comes from the propagation of that type from A1 to the strongly connected component, which happens to have A3 and B3 in there. It did not come from the initialization of the type propagation graph, but it came from propagating the types based on the edges that I have in my type propagation graph. Does that answer your question, Akalanka? Sure. Yeah. Yes. Right. Right, so notice here when I did the initialization of the nodes in my type propagation graph, I did not assign any types for A3 or B3, right? Because I know that these nodes will not exist anymore in my graph. They're going to be replaced by one node that is basically called the node A3 and B3, roughly speaking. So even if you do assign, any values to them, it doesn't matter anymore. Now we have a new node that contains basically two nodes together lumped in one component in the graph. So even if internally they may have some values, it doesn't matter. Once you strongly connect these components, everything will be lost for these internal nodes. Okay, no problem. Any other questions? All right, so now that we have discussed CHA, RTA, and VTA, let's discuss the fourth type of call graph analysis and the most precise of them all. It's a data flow propagation analysis called SPARC, and the name SPARC is just the name of that analysis in the SUT analysis framework, which we're going to see probably on the lecture on Thursday. The difference between VTA and SPARC, or data flow propagation, is in VTA we were tracking types across methods from allocation sites to potential references to variables, right? In SPARC, the main idea is slightly different. We are propagating information, not just the types, but information, pointer information, along the edges of a pointer assignment graph. So we no longer have a type propagation graph, but we have a more advanced or a richer graph called the pointer assignment graph. So I'm tracking the pointers across my program. I'm figuring out how they are assigned to each other based on maybe assignment statements, maybe method calls, maybe if statements, maybe new statements, and so on and so forth. I'm trying to figure out how that may affect the pointer and the pointers that are being passed around in the program. So SPARC was first initially introduced by Andrei Lotek, which happens to be my PhD advisor, and his PhD advisor, Laurie Hendren, back in 2003. And that was in an attempt to scale up pointer analysis for the Java language to be able to be used in practical settings. And that was published at Compiler Construction, or CC, in 2003. So you can look up that paper from either Google Scholar. Usually you can find the PDF there, or if you don't, you can always excuse me, you can always look it up on the ACM Digital Library, and you can, I think you can log in to the ACM Digital Library using the Easy Proxy service from the University of Alberta Library as well, so that you can just log in with your CCID credentials, and you can access the SEM digital library from there. So what does it mean, pointer assignment graph and tracking information or propagating information across the pointer assignment graph? So let me first introduce what the nodes and the edges that we're going to use, and then we might have actually a short break halfway through the class, and then we're going to continue from there on. So the nodes that we're going to have in our graph are going to be alloc nodes, showing constructors, var nodes, showing variables in the program, field reference or field ref, that basically shows a field reference that we may have in the program, a concrete field ref, where we actually know the base of that field access to be an exact specific object. In this case, it's new a.f. We have various types of edges in our pointer assignment graph. So we have an alloc edge that basically assigns or joins or connects an allocation site to a variable. An assign edge that basically tracks all those assignment statements between variables. So if you think of it, this here is basically what VTA does. But all the other stuff does not exist in VTA. So VTA only supports that type of one type of edges here from Spark. We also have store edges, and stores are basically storing values or writing values into some field, so from a local variable to a field. Loads are the reverse. You're reading a value from a field, storing it into a local variable. So again, alloc nodes are going to be modeling allocation sites in the program, and this basically, you will, for every single new statement in your program, you're going to have an alloc node. It definitely has a type, because you can see it right there in the instruction. In the SUT analysis framework, any type is basically means that the type is unknown. You don't know what that type is. Var nodes, they are going to represent variables that hold pointers to other objects. It doesn't have to be one pointer, it could be more than one pointer. We're going to use this var node to represent local variables, method parameters, throwable exceptions, and so on and so forth. It may or may not have a type, depending on what it stands for in the pointer assignment graph. A field ref node represents, like I said, a pointer dereference. So you are dereferencing or accessing a field of a pointer. The base of that field ref node has to be a var node. To handle a certain specific feature in Java, which is array contents, we have the special field ref node a.elements. So if you have an array A, we're going to have a field ref node a.elements to model all array contents of that array collectively. Again, this node here may or may not have a type, because P may or may not have a type. So depending on that, P.f may or may not have a type. Alloc edges, as I said before, they will model statements of the form P equals new A. So whenever you have an object being constructed, we're going to have an alloc edge between an alloc node and a var node. One thing to note is, not just in Java, but in any language, in many languages, allocation is actually independent of calling the constructor. So in Java, if you say A equals, if you say P equals new A, if you look at the bytecode, you will find that first you're going to see P equals new A, and then you're going to see P dot init in the bytecode. So two statements will happen. First, you construct the object, or you allocate the object, and second, you call the constructor of that object, so that you can populate its fields and so on. Alloc edges also happen, they basically induce constraints. So any edge that we have will generate constraints that will be solved later by our analysis. So in this case here, this basically generates the following constraints: that the points to set of new A will propagate, which is the information that we are propagating, will propagate to the points to set of B. And the way this is going to propagate is using the subset relationship. Again, why? because we are defining our join operator to be the union operator. So when I say the points to set of P join the points to set of new A, this is going to be the points to set of P union the points to set of new A. So this is why it was important for us to go through these definitions of lattice theory and defining what the join operator is and defining and figuring out how we can actually compute the joins and the meets of those items in our lattice. So now we know why it is a subset, so that we don't forget all the information in our program. And this here again will be just the regular assign edge between variables, and they will induce that or generate that constraint so that it was going to be solved later on by the analysis. Then we have a store edge. It basically models the assignment statement p.f equals q. So you are storing the value of q into p.f, and that's why the direction of the edges goes from q to p.f, and it generates the constraint that the points to set of q will flow to the points to set of p.f. The reverse of that is a load edge. So you're loading a value from a field into a variable, and then that's why you're generating a constraint that the points to set of q.f will be a subset of the points to set of p. So I'm gonna stop here for a few minutes and maybe continue again at 122 with how we're going to build the pointer assignment graph for this example, following all those definitions that we have just discussed. If you have any questions for me meanwhile, feel free to ask them on the chat or either by text or Zoom voice for those who are attending the class. And we're going to reconvene again in 4 or 5 minutes. All right, I am back. So let's continue with building a pointer assignment graph for this example. Before I move on, does anyone have any questions so far? Are we all good? All right, thumbs up are coming through. All right then, so let's actually build this pointer assignment graph for an example code. So we have this piece of code here, method foo, a bunch of constructors, a bunch of assignments, a bunch of field reads, and a method call, and then a method bar that is being called from method foo. So the first statement is going to be x equals new a. So we're going to create a node, an alloc node new a var node x, and we're going to have an alloc edge that joins between them. Second statement just says x is going to be assigned to y, so I'm going to have an edge from the var node x to the var node y. Third, I'm going to have z equals new a, so I'm going to create a node new a alloc node. I'm going to have a var node for z, and I'm going to connect new a to z. By the way, would there be any other way I can do this I can handle this statement? So if you notice, I created a new node for new a, another new a, I connected that to z. Do you think there could have been another way I can do this? More specifically, could I have just done that instead? And why or why not? Yeah, okay, so Robert is saying I could have connected the existing new a to z. So why didn't I do that? Because it is a new memory allocation, sure. They are different instances, sure. These are all plausible answers. But I could have still just connected this new a to z, right? If you look at the nodes, there is nothing that is differentiating between the first new a node and the second new a node. They look exactly the same. Like nothing here, for example, says, well, this is new a that is on line 3, and this is new a, on line 1, and this is new a that's on line 3. They are both exactly the same kind of node. So I could have gone away with just connecting that new a to z, and I could have still got a safe over approximation. But you're right. These are two different allocation sites. These are two different instances. So if I want my analysis to be as precise as I could be, I need to create two separate allocation sites for them, two separate alloc nodes for them. Yes, this would create more nodes and potentially more edges in my pointer assignment graph, but that's fine. I'm willing to sacrifice that larger expansion of the pointer assignment graph for the sake of having a more precise result. Again, this is one of those configuration parameters that you can fine-tune in your analysis, but still fit within the monotone data flow framework. So you can still configure your analysis to say, well, I want my analysis to differentiate between objects, meaning object sensitive, or I just want my analysis to treat all objects of the same type equally, to be the same, meaning it's going to be object insensitive, and I just want to get on with my life as such. Both are valid solutions. One is just more precise than the other. So we created, in this case, we opted for the more precise solution. So we created the new node for new a, connect that to z. Then moving on to the next statement, or the next line of code, x.f equals z. And here we just created a node for the field reference x.f, and this is a field right, so we're just creating, connecting that edge from z to x.f. Then we have a method called t.bar. So here a few things happen. So the first thing that happens when you call a method is this y implicitly is being assigned to that P here, right? So when you call a method, you have your actual argument, you're passing it along. What does that mean? It means that the formal argument of the method will receive or will be assigned the value of the actual argument. So in this case, I have to say y is going to flow to P. So even though there is no explicit assignment, it's an implicit one just by the fact that I'm calling that method with this argument. If here I had bar of A, I would have created a node A and then connected that to P. But I don't have that. So I'm not going to do that. The second thing is the following. The return, there is another implicit assignment that happens here. The return of that method is implicitly assigned to whatever the left-hand side of this assignment of that method is. So the return variable of bar is going to be assigned to T. What is the return variable of bar? It is P.f, so it is this. I'm going to assign it to T. Had this line been just bar of y without having the assignment, I wouldn't have created these nodes here, because even though yes, the method is returning a value, but it is not assigned to any variable in foo, so there's no need to do that. But again, I cannot do that because I cannot ignore this assignment because I do have an explicit assignment statement here to T. Cool, so now I have all these nodes and edges here. So a question for you. Can you tell, just looking at this graph here, whether I could connect x.f to p.f? So if I advance forward with my pointer assignment graph, do you think that x.f would point to p.f? Why or why not? I'll give you a couple of minutes to think about this. You can also ask me questions if, in case you're not sure about something. So we have one yes. Any other yeses or no's? Okay, so the yes is because when we assign x to y, x.f flows to y.f. True. And then we call bar y, okay. And y.f flows to p.f. Yes, exactly. So indeed, it is going to be true. So let's actually walk through the solution that Ridwan just wrote on the chat. And we'll go through it step by step to figure out exactly how we can deduce this from the analysis, even though might not be that obvious just looking at the pointer assignment graph as such. So before we do that, we need to figure out first to talk about the differences between handling fields in different ways, three main ways to handle fields in an analysis. First, the analysis could be field sensitive, meaning that I am going to differentiate between accessing the field F in A and accessing the field G in A and accessing the field H in A. These are going to be three different field accesses. I'm not going to treat them the same way. Each one of them is different. On the other hand, fields insensitive will just say A.F to me is the same as A.G, the same as A.H, the same as A.anything. Any field I'm accessing in A is going to be treated the same. I don't care what the field is, I only care about that it is a field access. So this is called field insensitive. Field-based, on the other hand, does care about accessing the field, but does not care about how you're accessing it. So I don't care, to me A.A1.F is the same as A2.F, is the same as, I should actually use equals here, is the same as A3.F, is the same as A4.F. That is what field-based is. So in both field-sensitive and field-based, I do care about the field. Field-insensitive does not care about the field. In both field-sensitive and field-insensitive, I do care about the base of the field axis. I need to have a specific concrete object. In the field-based, I don't care about that object. I'm just going to use the class name to differentiate accessing those fields. So this is an important distinction, and yet, again, one of those knobs that you can configure in your analysis to produce or generate a different over approximation that is still sound or valid, complete solution, but with a different precision. So it lies down at a different part of that green spectrum of valid solutions in the lattice of solutions for call graphs. Other considerations that we need to consider in the pointer assignment graph is static initializers, because in a language like Java, static initializers are called basically once at the first axis of a certain class. Object.finalize, so this is a method that is called implicitly by the Java runtime on certain fields that have on certain fields based on the specification of the Java runtime. Thread.start, so threading, multi-threaded programs, you need to handle that as well properly. And reflection, of course, which is a way of dynamically accessing fields and methods by calling them, assigning values to fields, reading values from fields, accessing private class members, and so on and so forth. All these considerations, you have to make sure that you take them into account when you're creating the pointer assignment graph, because they will affect the creation of the pointers, the propagation of the pointer information from one statement to the other. And if you don't, then you just don't support one important feature of the language, and the analysis designer needs to be aware of that so that they know how they can use the results of the analysis in the appropriate context. We talked already about object sensitivity when we talked about the two nodes new A. So going back here, the points to propagation step of the pointer assignment of Spark is going to be as follows. Now I'm giving labels to those nodes A1 and A2, because now I know my analysis is object sensitive, so I need to give them separate labels. And I'm going to assign or basically propagate my pointers along the statements. For the first statement, I'm just going to say, okay, what is going to be my points to set? Remember those constraints that are induced by certain edges by the edges in my pointer assignment graph? I'm basically going to follow along these edges. So in the first edge here, it just says that the points to set of X is going to be the points to set of new A, which is basically the set of that object A1. So this is what my first statement does. In the second statement, I'm going to say, what is my points to set for y? Well, it is the same. It is going to be the set of the points to set of x union the existing points to set of y. The existing points to set of y is empty, so it's the empty set union the points to set of x, which is a1, so it's going to be the set a1. For z, it is going to be the set a2, because it is just the initial set that I have from that new node, new a. For x to the f, it becomes a little bit more interesting. The points to set of x to the f is basically, so I can write this as follows. Nope. How can I erase this? Okay, that's fine. So I'm going to write that the points to set of x to the f is basically the points to set of x dot f, right? So what is the points to set of x? Well, it is the points to set of that's not what I want. Something is wrong on these slides here. Right. So what I need to do here is the following. So this here according to this statement, this says that the points to set of x at f would be the points to set of z, right? And the points to set of z is the set a2, right? However, I can actually rewrite the points to set of x dot f to be the points to set of x dot f, which is the same as, what is the points to set of x? Well, the points to set of x is that set a1. So I can just say, okay, it is going to be the points to set of a1 dot f. And I already said that this is going to be is equal to a2, right? So keep that in mind for now. So the points to set of x dot f is the points to set of z is going to be a2. I can rewrite the points to set of x dot f to be the points to set of x dot f. So it is going to be why is the eraser here? It is going to be the points to set of a1 dot f, and I can say that this is also equivalent, so it will be a2. So keeping that in mind, let's move on. The next statement, this method call that we have, is going to assign the points to set of y to p. So the points to set of p will be the points to set of y, so it's going to be a1. And again, that return is going to assign p dot f, and at that point I can say the following. I can say similarly, the points to set of p dot f is going to be the same as the points to set of p dot f. And what is the points to set of p? It is going to be the points to set of y, right? Dot f. And what is the points to set of y dot f? It is going to be the points to set of a1 dot f. And remember, from here we said that the points to set of a1 dot f is the same as x dot f, and it's going to be a2. So I can just say that this is going to be as well a2. And now I can finally deduce this edge here. So I can add this edge. So the pointer assignment graph in the propagation step, after the initial values have been assigned to the nodes on the edges, I'm basically trying to deduce which further edges I need to add to my pointer assignment graph. So I'll keep adding edges as I go, depending on the constraints that are being generated and being solved for in my analysis. So this is the more kind of formal deduction of how this relationship will come about, which basically matches those 3 lines that Ridwan sent on the Zoom chat. So far, so good. Any questions? All right. So going back to the main method, we're going to now have the assignment of p.f to go back to t. So the points to set of t will be a2. And that will be all the pointers, all the propagation of the pointers that I have in my program. So now for every single variable in the program, this is going to be the result of the analysis. For every single variable in the program, x, y, z, x.f, p.f, and t, I can tell you right away what would be the objects, the set of objects that this variable may point to at runtime. So that if you have a method call like x.baz or something, I can tell you exactly, well, it's the points to set of x. So baz here that would be called would have to be the baz method in the object a1, which is of type A. So this has to be a.baz. Cannot be any other method. It has to be a.baz, based on the propagation and the tracking of the pointers across the program and how they are assigned to each other and how they flow from one to the other. So now I can tell you what the call graph result is, or what the call graph is. So pros of that Spark data flow propagation graph is it is very precise. I can get to the point, the granularity of the pointers that are being propagated and passed through in my program. It's highly customizable, as we have seen. You can change how it is handling arrays, you can change how it's handling objects, you can change how it's handling fields, so it's highly customizable. The big win here is that we don't need an initial call graph. We haven't started our analysis or bootstrapped it with an initial CHA or RT call graph like VTA, for example. However, the analysis is flow insensitive. It is quite expensive. We're doing a whole lot of tracking of pointers and data flow in the program. So we're doing a lot of extensive computation. And the pointer assignment graph can get actually quite large, prohibitively large, because of all the nodes that are being represented there, all the edges that are being represented there. And the more precision that the more precise that you want your analysis to be, the larger the pointer assignment graph would be, and the more prohibitively expensive it will become. So these are some of the pros and cons of the Spark data flow propagation analysis. Any questions so far about CHA, RTA, VTA, or Spark? We're actually almost close to the end of the lecture, so I would rather discuss the next. We have only just a few more slides regarding call graph construction, but I would rather discuss them all in one segment of our lecture. So I'll defer that to our lecture on Thursday. And on Thursday, after we're done with that small part of call graphs, we're going to actually go through some coding in class. So I'm going to show you how you can code some analyses to generate call graphs, CHA, RTA, VTA, and Spark, and a few others as well that we haven't seen in the class, using some of the analysis frameworks like Soot and Wala, and how they actually compare to each other on a whole bunch of applications and programs that we're going to see in class. I do have the link to the repository that contained the code that I'm going to use in class available on eClass. So if you want to check it out and find it's in the resources, it's under the resources, under the resources label. I think it's the second link under the resources label. So check it out and make sure that you have it handy for our lecture next week. And yeah, that's all I have for today. Do you have any questions for me before we end our Zoom lecture today? All right. I don't think anyone has any questions so far. So if that's it, then I'd like to thank you all, and I look forward to having you again on Thursday. Have a good day, everyone.